For decades, enterprise risk management focused on the perimeter. But as digital transformation accelerates, danger emerges from within, a byproduct of speed called internal entropy. When an organization connects, automates, and integrates at high velocities, it creates a new topography of risk. Every integration is a decision about trust. Every automation inherits the assumptions of its designer. The result is internal friction that threatens structural stability. Silicon-based systems are built on the logic of the industrial era: stability through redundancy and the elimination of variance. Engineers spend billions of dollars trying to scrub out noise. Biological systems operate on a different set of rules. They do the exact opposite, actively harnessing environmental noise to survive and thrive. This suggests that true system resilience isn't found in rigid order, but in how an architecture manages its own internal chaos. Near beginning to see the limits of rigid order in generative AI, researchers have identified a specific failure mode threatening these systems: model autophagy disorder, or Habsburg AI. Model autophagy occurs when generative models are trained recursively on their own synthetic data. Without a constant stream of fresh human input, the system begins to feed on its own outputs. The functional degradation is measurable. A model that starts with highly factual responses eventually begins hallucinating nonsensical artifacts until the output is useless. This happens because algorithms are designed to sample for high-probability patterns. In a closed loop, they systematically ignore the rare, low-probability nuances of human reality. Preventing this algorithmic collapse requires digital systems to mimic the survival mechanisms found in biology. Human variability and noise are being reconceptualized. Instead of a computational liability, engineers are exploring noise as a possible engine of systemic resilience. This 3D scatterplot visualizes the vector space of a large language model. The dense cluster in the center represents the average of human knowledge. The sparse outer points are the long tail. These represent the statistical outliers, the edge cases and minority data that provide true human nuance. In a recursive training loop, the AI generates new data and feeds it back into the set. Because the algorithm prioritizes certainty, it pulls almost exclusively from the dense center, bypassing the edges entirely. This initiates early collapse. The distribution violently narrows as the system systematically severs the long tail of minority data. During late collapse or digital dementia, even that central spike shatters. The data shuffles into disorganized noise, rendering the model permanently broken. The mechanics of this breakdown indicate that generative models favor mathematically high probability patterns over complex reality. By running on a loop, this process industrializes omission. It amplifies bias at an exponential scale by repeatedly choosing the most likely answer. The mathematical severing of human nuance suggests that unanchored AI possesses a natural tendency to destroy its own foundational intelligence. At the enterprise level, this statistical decay manifests as data drift. Data drift occurs when automated systems become unanchored from the friction of lived human reality. The informational fabric of the system moves faster than the frameworks meant to understand it. This unmonitored accumulation creates ethical debt. Without human oversight, systems mathematically amplify bias, paying the interest in the loss of trust from customers and regulators. This debt compounds because of governance lag, the delay between what a system can do and what leadership understands it to be doing. Oversight models optimized for static, industrial-age compliance are often blind to this endogenous degradation. In the microscopic world, cellular systems operate aggressively far from thermodynamic equilibrium. They do not seek a state of rest, they seek constant directed activity. A clear example of this is the Fenner-Matthews-Olson complex, a protein structure found in photosynthetic bacteria. The FMO complex transfers absorbed light energy to a reaction center with near-perfect efficiency. To do this, the energy must find the optimal path through an incredibly chaotic, noisy molecular environment. Biology manages this through stochastic quantum jumps and proton tunneling. The energy packet probes all possible pathways through the vibrating network simultaneously. The biological system harnesses random thermal noise to physically push the energy along the most efficient path. Direct comparison shows that in biology, pure static order is fragile and energetically expensive. The FMO complex demonstrates how utilizing quantum uncertainty and thermal noise is essential to maintaining systemic structural coherence. This biological resilience is summarized by the constrained disorder principle, or CDP. The principle posits that internal and external noise are not defects, but mandatory inputs for proper system functioning. The caveat is that this disorder must be kept strictly within dynamic, adaptable boundaries. AI's current crisis represents a departure from this principle, a rigid pursuit of pure order that leads directly to brittleness. True architectural resilience requires dynamically constrained chaos. This is a law that silicon systems are now beginning to adopt. To combat model collapse, researchers are introducing a radical architectural shift. Engineers realize they must artificially inject the very disorder they once tried to eliminate. One solution is active inheritance, a digital equivalent of a biological dynamic boundary. Active inheritance mathematically blocks the model from following the most probable path. It forces the system to select high-entropy, diverse data instead. A secondary method is best-of-k filtering. This protocol generates multiple outputs for a single prompt and grades them for informational density rather than statistical likelihood. These techniques artificially recreate and sustain the long tail of human nuance within the machine's architecture. This mathematically enforced variance prevents a closed-loop automated system from suffocating on its own predictability. The ultimate anchor for these systems is the vault strategy. The vault strategy isolates pristine pre-2023 human-generated data to serve as an immutable, non-synthetic baseline for future training. To connect the model back to this baseline during live operation, engineers rely on reinforcement learning from human feedback, or RLHF. RLHF functions as an ethical circuit, a feedback architecture that applies the dynamic boundaries of the constrained disorder principle directly to silicon. The invisible frontier of digital risk has shifted. Danger is now a condition of internal entropy rather than an event of external threat. The survival of any intelligent system relies on the continuous injection of constrained disorder. The most resilient architectures are not those that reject the messy noise of human reality, but those that are permanently anchored by it.